máster con Javier Bustamante y conmigo, enmarcado en el proyecto Ecopotencia. Va a hacer la presentación en inglés porque es la misma presentación que va a hacer en la defensa del máster en Holanda.
Thank you to come here. As Luis said, I will present my research project of my master. And I start right away. A short introduction. As we say, the project it's in the Doñana marsh, and as you know, the Doñana marsh is a very important ecosystem and very important wetland mainly because it's a sanctuary of birds, but also the Doñana marsh provides a lot of other local and regional ecosystem service. And although it's important, there is some human impacts that affect the marsh. One of it, specifically for the vegetation, is that there is some authors that argue that there is an overexploitation of the biomass by the herbivores. And at the end, the biomass is the bottom of the food chain of any ecosystem. Specifically, the tubers of Bolbogenus maritimus, that is the main plant, the predominant plant in the marsh, it's the food source of the migrant geese. What we have done in this project is using remote sensing techniques. We model the biomass production and also we study the different dynamics of the vegetation. We did that in 4 different steps. First, we model the phenology. Secondly, we calibrate the model. Third, we validate this model. And at the end, we study the spatial patterns and the temporal patterns of the biomass production. A bit more of the study area. Well, the Doñana marsh has an area of 340 square kilometers, and it's a very heterogenic marsh, mainly because the flooding regime is controlled by the rainfall. And as you see in this graph here in the bottom, the rainfall is also very heterogenic. To try to have a most homogenic area from all the marsh, we choose those areas of Bolbogenetum maritimi area, that is the phenological association, the predominant phenological association of the marsh. Although it's important, there is very few estimations of the amount of biomass that is produced. There is some articles that mention in some specific times, but really we don't know how much biomass there is in the Doñana marsh. At the end, this is the final study area that we use. I will talk a bit more about the data that we use. We use remote sensing data. Of remote sensing data, we use the NDVI product of MODIS. For who doesn't know, the NDVI, it's the near-infrared red reflectance ratio. MODIS gives us an image every 16 days. And we have information since 2000 till the present day. About the biomass data that we use in this project, we use 2 different sets of data, one to calibrate the model and the other one to validate the model. To calibrate the model, we use a set of data provided by Ramon Xuriguer that consists in estimations of biomass production in 5 different locations that are marked here in this map with red squares. To validate the model, we collect our own data, and I will explain the fieldwork design in the next slide. A part of that, we use 2 sets of complementary data, environmental data. One, the hydro period, that is the amount of days that each pixel is flooded, provided by the last, and the precipitation. I will explain a bit the fieldwork design. First, what we did was to classify the study area in 3 different categories: high values of NDVI, medium values of NDVI, and low values of NDVI. We did this step because we wanted to have all the range of productivity that we could find in the marsh. This classification has been done with all the historical NDVI values. In each one of these in each one of these categories, we select randomly 3 MODIS pixels. This makes 9 MODIS pixels. And because we think that this data that we collect can be used in the future with other remote sensing data, we also incorporate Landsat. Then, in each MODIS pixels, we select randomly 3 Landsat pixels, and in each Landsat pixels, we select 4 sampling points. This makes 108 sampling points of 1 square meter. In these sampling points, what we did was to cut all the biomass. After we sorted by species, we weighted, we dried it, and we weighted again to have estimations of the biomass production per pixel. I will explain briefly the methodology in all the 4 steps that I talked before. First, we model the phenology of the vegetation. We did that with land surface phenology. This is a technique that studies the timetable development of the vegetation. Specifically, what it measures is the photosynthetical activity of the vegetation. We did that with a program called TimeSat that is specific to analyze time series. And what TimeSat does is, well, there is 3 options of curve, 3 options to model this NDVI curve. I will talk a bit later about these 3 methods that TimeSat use. And at the end, you obtain the metrics of this curve. The metrics that we were interested were the maximum NDVI value and the integrated of the NDVI curve. Apart of that, because the marsh is a complex ecosystem, we have to manually adjust some of the parameters that TimeSat offers. I will talk a bit later about that. After that, we calibrate the model. And in this step, at the end, what we did is to test different options, to test what it works and what doesn't work. First, we test which of the fitting models of TimeSat works better, the Slavitsky-Golait, the Gaussian, or the double logistic. Second, we test which metrics work better, and also not only which metrics works better. We also test if the relation between the biomass and these metrics was a linear relation or non-linear relation. The third step was to see if part of the variability that we find in the model could be explained also for environmental variables. And at the end, we test how robust was our model, regardless the production in each one of the locations. What we find in the data of Ramon is that each location had different productivities, and we wanted to test if our model works better in the different productivity range. The third and fourth step was to validate the model. As I said before, we validate the model with data of 2016, with the NDVI data of 2016, and also with the data that we collect in the fieldwork campaign. And the last step was to analyze the patterns of production and distribution. The first step was to look to the maps that we produce, but to try to summarize this information, we applied an estimator that calculates the slope, and it says where the precipitation increased and where the vegetation increased and where the vegetation decreased. Also, to try to study the temporal variation, we compare this temporal variation with patterns of precipitation. And yeah, here we start with the results. First of all, I said before, we had to adjust manually some parameters of TimeSat. We did that because here in the top, you see the graph of the NDVI in a wet year in the marsh, and you see a decrease, a drop in the curve in the month of January that stay low till the months of March, April, depending on the year. And this drop is not representative of the photosynthetical activity. This drop represents the water. When we include this raw graph to TimeSat, TimeSat gives a very strange results, as you see. This is why we decided to cut the influence of the water, and for that we apply an NDVI of 0.27, that is the value of the dry vegetation. Also, we had to determine when the start and the end of the season, where is the start and the end of the season, and after trying several options that TimesAnt offer, we decided to fix this value in the 10% of the amplitude of the curve. Here we start the calibration, and the first step was to see, okay, from these three methods that TimesAnt used to model the NDVI curve, which one gives us better results in relation to the biomass production. We test the three models, and we conclude that the Slavinsky-Golait filter was the one that gives better results, and this is why we choose this method. After we compare the two different metrics, the maximum value and the integrate value, and we see that both give us pretty similar results. And after taking a look to the data, we see that probably the relation between these metrics and the biomass was not a linear relation. And then is why we apply the natural logarithm. This model that it's marked with an arrow, it's the model that we use to produce our maps, because it's the one that gives a better adjustment. At that moment, because we decided to use the maximum NDVI, at that moment we wonder why we have modeled the maximum value, why we don't use the real number that the NDVI gives you, this single value that is the maximum. What we did is to see the raw data of NDVI, extract this max value, and what we find is that without modeling, there is no relation. This, what it tells us, is that all the modeling of the phenological curve was necessary. Other two things that we try, as I say, first we try if an environmental variable could explain part of the variability that we find in the model, and we add precipitation and hydroperiod as a covariable, but the results show that these variables were not significant. The last thing that we try is what I was talking in the methodology. Because each location had different productivity values, we wanted to see if the behavior of this location was different in relation to the NDVI. And what we test that using a model with interaction and without interaction. What that means is a model that has different slopes and different intercepts, or a model that has different intercepts but one slope. If we compare these two models, they are not significant between each other, and this led us to think that although the intercepts can be different, because the base level of biomass is different, the behavior is the same. These are the results of the field work. As I said before, we collect 108 plots, and this represents 40 kilos of biomass that we extract from the marsh. This value is from dry biomass. The rest of the results are from, these results are from wet biomass. The rest of the results is from dry biomass. But yeah, it was quite a lot of vegetation that we take from the marsh. The first things to notice is there is a lot of variations of production between locations. We have places that we have less than 500 kilos per hectare, while we have areas that we have almost 3,000 kilos per hectare. And the second thing that surprised us was the high variability on a species composition. As I said at the beginning, we were expecting to have mainly Bolbochenus maritimus, but when we went to the field, these only represent the 47% of the biomass that we collected. And yeah, this is the validation. When we test the measured values with the predicted values, we find a regression that have a fitting of 0.7. It's not a great result, but it's enough to say that our model is valid. Here we test also is if the slope of this regression line was significantly different than 1, and the result was no. The slope is not significantly different than 1. This means that our model neither overestimates the biomass production. Once, because we see this variability among species composition, we wanted to test if our model could work better in areas where more percentage of Volvocenos maritimus. This is why we add as a covariance the proportion of Volvocenos maritimus. And this was not significant. This means that our model works exactly the same in areas with high presence of Volvocenos maritimus and with low presence of Volvocenos maritimus. Yeah, finally, because the model was valid, we could estimate the biomass production of all the study area and from all the years of our study, from 2001 till 2016. The first things to notice in these maps, it's the high variability in production. For example, we have years as 2005 that we almost didn't have any production of biomass, only in the northern areas, and the values are very low, around 200 kilos per hectare, and years like 2010 that the production increased to more than 10,000 kilos. The other thing is the spatial heterogeneity. For example, in years like 2001, we have maximum values. The maximum values are located in the south, while years like 2010, the maximum values are located in the northern part. As a first impression of this march, we could not observe any clear pattern of distribution. To try to summarize this information, what we have done is to apply the Thames-N slope estimator, that is this map that you find in the left. What it's marking in red, it marks the area where there is a decrease in production throughout the years, and in green, it shows the areas where there is an increase of the vegetation. In general, it's possible to say that in the central areas, the vegetation is decreasing, and in the border areas, the vegetation is increasing. If you juxtapose this map with the average biomass production for these 15 years, in general, it's possible to say that in areas with more production, the vegetation is decreasing, and in areas with less production, the borders, the vegetation is increasing. Although this is true, and you could see it in these maps, it's important to carefully interpret the results, and I will discuss this later in the discussion section. To try to explain, this is the last analysis that we did, and we wanted to try to explain the temporal variability that we see in the maps. And for that, we compare the average biomass production per year with the precipitation. First, we test which month had more influence on the biomass production. We test different intervals, and after testing different intervals, we see that the months that really have influence in the biomass production is from September to April. And this could explain the 51% of the variability. But seeing these two curves, that one is the precipitation and the other one of the biomass, we realize that when the precipitation is low, it's really correlated with the biomass production. But when the precipitation is high, the correlation is lost. For that, we test this, and what we see in this small table on the bottom is that when we have low precipitation, we have a linear correlation, a very clear linear correlation, but to certain threshold, this linear correlation, it's completely lost. I enter in the discussion section. Here I will emphasize some of the most important things that we see in the results. I think that it's very important, the idea of that the process of modeling the phenological curve was necessary, because if we didn't do this step, we would not find any correlation between the NDVI and the biomass production. Also important to mention that the Slavinsky-Golait technique is the one that better works for us. And also this is consistent to most of the authors that also argue that this is the best fitting method. We find this proxy between the NDVI and the biomass production. A lot of authors find the same proxy, but it's important to say that this also happened in the Doñana marsh, and that both the maximum and the integrate value give similar results. Why we choose to use the maximum value is because with the maximum value, we could have the predictions of the biomass around the month of April, May, and if we use the integrate value, we have to wait till the end of the season. We think that it's interesting to have these predictions in the months of April and May. And yet, to say that there is a non-linear relation between these metrics and the biomass production. Other things important is that the relation between the NDVI and the biomass production, it's not influenced for environmental factors. It's a one variable relation. Also, this test that we did for the different locations with the categorical, adding location as a categorical variable, I think that is very interesting, because if once in some moment we could have a classification of the marsh by production, we could apply these models and we'll improve. We will improve the results. We think, and as we read in different articles, that the mix of a species composition make that our model is not that good, and a lot of authors at that moment, what they are trying is to do monospecific models, but with the data set that we had, this was not possible. But yeah, at the end, anyway, there is a high heterogeneity in production distribution, especially and temporally. We think that part of this heterogeneity could be explained by the precipitation, and probably with the Erio period, we could be able to understand more all this heterogeneity. As I say, although the results have to be interpreted carefully, because there is a lot of confounding factors that could influence. For example, this year, the presence of Azolla, that is an invasive species. We had NDVI image with very high values of NDVI in the north, but because the people from the LAS know where Azolla was located, we could relate these values to Azolla and not to the biomass production. I think that this is only one example of things that one has to be careful when interpreting the results. The last things that I want to say is that, monitoring wetlands, it's complex because you have an interplay between water, vegetation, and soil. And specifically in Doñana, this becomes more difficult and more challenging for the presence of cattle. That also interplays with water and vegetation. For example, cattle are not distributed uniformly in all the marsh. For example, cattle in dry years will concentrate in the areas where there is wells, while in very wet years, cattle don't have access to some areas that in the marsh because are flooded. Also, cattle will concentrate in areas with more production of biomass, but this at the end will reduce the yields. We think that this project could be a starting point and can be improved with other sorts of remote sensing techniques. For example, using Landsat or Sentinel can reduce the scale of the project, because now we are using MODIS that have a much bigger pixel. Also, there is other authors that are using LIDAR or radar to do this type of models. But at the end, we think that this analysis of time series is very interesting because allows you to observe the changes in the time and to find cause effects events. To finalize, I want to acknowledge the supervisors, Javier Bustamante, Luis Santamaria, and Gerrit Hale. I really learned a lot during this project. Thank you. To the last, because they helped me in so many moments, to David Aragonés, Isabel Afán, Ricardo Díaz Delgado, and Diego Garcia, and also because they feel the last my home, and in general to the EBD, Alfredo Chico y José Luis del Valle that helped me during the field work, Rocío Fernández that helped me in the vegetation, in the plant identification, and to Irene Paredes.